Okay, we'll get started here. Well, I guess before I get started with the lecture content, just want to check if there's any questions regarding logistics or things like that. You have both options for homework 5 posted now, so you can choose between the Monopoly coding assignment or the Bootstrap randomization test assignment. Okay, and that's just due next week when homework 5 is due. So you will, whichever one you choose, you'll render your homework and submit it under homework 5, and then the graders will, when they open it, will figure out which one you did. Okay, and so that's how we'll do that. Is that okay? Any other questions? Students have been asking about the final exam. The final exam will look nothing like the midterm exam, okay? It's going to cover stuff from after the midterm, so it's going to cover numeric methods. Do you understand these root finding methods? Do you understand these optimization methods? Do you understand the bootstrap and the randomization test procedures? So that's what the final exam will cover, and I'll talk about that next week, as the final approaches. Anyway, that's that. Okay. We're all good? No questions? Okay, we'll get started then. We'll talk about Bootstrap. So far we've covered randomization tests as a way to do hypothesis testing when you have a random assignment. And bootstrapping is another way to do either hypothesis tests or learn about the sampling distribution, but it's different, okay? All right, so bootstrapping, it comes from the phrase "pull yourself up by your bootstraps," and if you try to look into the origins of this phrase itself, there's questionable stories and whatnot. The one that I like is the one where there's the folk hero. He was stuck in a swamp, and the way he pulled himself out of the swamp was he pulled himself out by his bootstraps, which, of course, that doesn't make sense. But anyway, that's what he did, right? Okay, and in statistics, bootstrapping is, at its core, it's a resampling method. Okay, much like a randomization test is a resampling method, bootstrapping is another resampling method. Okay, and these fall under the umbrella of computational statistics because both methods, randomization tests and bootstrapping, require thousands of replications of resampling. And doing something like that is only possible with the aid of a computer. You would not physically be able to produce, 1,000 random samples manually in any kind of way. If you go back 50 or 60 years, people didn't have a computer that generated random numbers, and so you would actually purchase these tomes of random digits. It would be like the size of a dictionary, and every single page would just be, like 1,000 random digits, and you could do something like set seed by saying we're going to start at page 457, and you'd say I'm going to start at the first column, first line, and you would just use those as a way to have random digits. Okay, and that's what people did, right? And then we have computers now that give us high quality pseudo-random numbers. There's a lot of history that goes into generating random numbers, which we take for granted today. Today we have the Mersenne twister, which is kind of our default random number generator. But anyway, that's all covered in 102C, Monte Carlo methods and whatnot. Well, okay, but anyway, bootstrapping is a resampling method. We can use it to test hypotheses or make conclusions about the population. without the need for additional data, right? We're trying to get a sense of what the sampling distribution is without seeing the population, okay? So maybe before I continue on, can someone explain what a sampling distribution is? Yeah, go ahead in the back. Yeah, it's the idea of how the sample statistic, whether that be your sample mean x bar or your sample standard deviation s or whatever it might be, what is the distribution of x bar if we were to take different random samples from the mean, okay? And so probably in your intro stats, your stats 10 class, you learned that if the population, no matter what the shape is, if the population has a mean of 100 and a standard deviation of 20, if you take random samples of, say, size 16 and we look at the mean, the sample mean, you know, your first random sample that you take, maybe just by random chance you get some values, you get a sample with a mean of 97.6 or something like that, okay? And then if somebody else took a random sample of 16 from the same population, maybe they get 104.5, okay? Someone else takes another random sample, they get 100.2. Someone else takes a random sample, they get 110.2, okay? And the sampling distribution is which values of x bar will appear more frequently and which ones will appear less frequently. And in stats 10, you learned that when you're looking at the sample mean, no matter what the population looks like, the sampling distribution of the sample mean follows what? A normal distribution, okay? And it's going to have the same mean as the population and will have a standard deviation or standard error of s divided by the square root of n, okay? And so you would end up getting a normal distribution with a mean of 100 and a standard deviation of 20 divided by the square root of 16, standard deviation of 5. Okay, and we use that fact to do all of our inference, to do things like the t-test and all of that. Okay, but in order to kind of experimentally produce that sampling distribution, we had to know the properties of the population. Okay, we had to be able to draw random samples from the population repeatedly. With bootstrapping, what we want to do is we want to get the sampling distribution. We want to know what that sampling distribution looks like without actually collecting more data from the population. Okay? How can we do something like that? Okay. Okay, so we'll talk about that. Let me just do a quick comparison between Bootstrap resampling versus the randomization test. So on Monday we talked about the randomization test, and it sounds all kind of similar because we are resampling in both of these things. The key difference is that we do randomization tests when the data was obtained via an experiment where random assignment is used. Okay? So if we did an experiment and there was random assignment of the treatments, the appropriate thing to do is a randomization test. If the data was obtained via random sampling from the population, then you can use Bootstrap. Okay? So how we obtained the data is going to determine which method is appropriate. We do a randomization test if there was random assignment of treatments, because that allows for the assumption of exchangeability. Whereas if we use random sampling to draw our sample from the population, the assumption of exchangeability no longer applies, and we can, but we have a random sample and we can use Bootstrap. Okay. In both cases, we are going to use randomization, okay, or kind of the computer's ability to randomize as our source of variation, okay? So we're either going to redo the random assignment, which is what's done when we do a randomization test, or we're going to simulate redoing the random sampling, which is what we do when we do Bootstrap. Okay. There's parametric and there's non-parametric bootstrap. Okay. Parametric bootstrap is the one where we put the most assumptions, we make the most assumptions about the population. Okay? In parametric bootstrap, we say, I believe the population has this distribution. I believe the population is normally distributed. Or I believe the population has an exponential distribution. Or I believe the population has a hypergeometric distribution or something like that. Okay? And so that requires your understanding of the population, okay? And whatnot, right? So when would it be appropriate to use the exponential distribution? Wait times, okay? Or how long a component lasts, right? Time to failure is exponential distribution, things like that, okay? Or, based on your understanding, you might say, this is a situation where I think the Poisson distribution makes sense, right? And when do we use the Poisson distribution? Yes. Yeah, how many times an event happens over an interval of time, right? So like how many phone calls come in the next hour? How many people show up in line at the bank teller in the next 30 minutes, right? Those are your classic Poisson distribution examples. And so if you are getting data from one of those classic situations, you can say, oh, what I've learned in Stats 100A and we still remember, I can apply the Poisson distribution in this situation, or I can apply the exponential distribution in this situation. And in those cases, it makes sense to do parametric bootstrap, okay? And what you do is you say, okay, based on my sample of data, I can get an estimate of these parameters, right? I can get an estimate of what lambda should be for if we're dealing with the exponential or Poisson distribution based on what I see in my data. Using that estimate, we just set up this random distribution in R, and we draw random samples from the specified parametric distribution. Okay? So for example, let's say you are trying to do, you want to generate random samples, and we're talking about, how many phone calls came in the last hour. And so you've got all this data from some phone center, and they say, this is what we have. And based on that, you say, okay, based on the data I have, my estimate is that for the time between noon and 1 o'clock, I have a lambda of 15, okay? And so basically, you would just go to R, and you would say, R Poisson, okay, because that's R's method for generating a random sample from the Poisson distribution, and you say, give me random data, okay? And that's what parametric bootstrap is, okay? We just simulate many random samples from whatever specified population that we have, okay? So here you are assuming that the population follows a particular parametric distribution. Now, if your assumption is a bad assumption, right? So you learned something that the number of phone calls that appear in an hour of time should follow the Poisson distribution. That could be wrong, right? You could have a situation that's different, and then everything falls apart. But if you're confident about the distribution that's generating your data, parametric bootstrap is appropriate there. Okay, and this is going to generate just random samples from there, and with those random samples generated, we can get estimates of this sampling distribution and whatnot. Does that make sense for parametric bootstrap? Okay. With non-parametric bootstrap, we are not going to make any assumptions on the distribution of the population. Okay, we gather data, and we're not going to say, oh, based on what I know about the situation, I believe that our population follows this distribution. We're not going to say that. We're just going to say, here is my random sample of data. The key here is that the sample that we have, we are going to assume is a random sample from the population. Therefore, we can expect it to be representative of the population. That's the key assumption and leap that we are going to be making. Okay? We're going to say, I have a random sample of data. Because it's a random sample, I'm going to assume this is representative of the population. Okay? And so someone says, you know what? I don't have the actual population, but I want to get a sampling distribution. So what we do is we say, okay, you know what? I have my random sample. I'm just going to create 1,000,000 duplicates of my random sample. Basically, I'm going to just multiply my random sample by 1,000,000 or 100,000 or whatever it is, okay? And this will be my stand-in for what the population is, okay? So it would be as if it's kind of like the idea of, you know, you're trying to like draw a forest or something on the computer, and all you do is you just have a picture of one part of the forest, and so you just say, I'm going to just copy and paste this, and I'm going to paste this everywhere, and then you get something that looks kind of like a forest, okay? So if there's any weird quirks that show up in that one patch of forest that you copied and pasted, that's going to show up everywhere in your, quote, population that you've made up, okay? What we're hoping for is that your random sample is indeed representative, and so when you duplicate it, you are going to get something that looks kind of like the entire population. Okay? And so effectively, instead of actually having to duplicate the data 1,000,000 times, all we do is we just take our sample and we resample it with replacement. Okay, so we just take an observation, then we put it back, and then we take another observation and we put it back. Okay, so sampling with replacement is effectively the exact same thing as just having a 1,000,000 duplicates or an infinite number of duplicates of our sample. Does that kind of make sense? So non-parametric bootstrap, we sample with replacement, and that is effectively just taking your current random sample and making thousands of duplicates of it. Okay, and then when you do that, then you can get something that should look like your sampling distribution. Okay, so I'm going to use the example that comes in your Ziefler textbook. Okay, so this is a textbook that you have free access to via the UCLA network. And we are going to take a look at this file called latinoeducation.csv, okay? And this is coming from the US Census Bureau. We're looking at immigrant population of people from, immigrants coming from Latin America. And we want to see, is there a difference between the education achievement of immigrants coming from Mexico versus immigrants coming from other Latin American countries, okay? So the US Census Bureau decided to do this kind of study, and they are, so the data that we have are immigrants coming from Latin American countries, and we have separated those coming from Mexico from those coming from other Latin American countries, okay? And if you look at the data dictionary, the value that we are going to be interested in is this thing that says educational achievement level, okay? And this is a scale of educational achievement, and it ranges from 1 to 100, where higher values indicate higher levels of educational achievement. Unfortunately, it does not actually tell us what these numbers mean, okay? So does 100 mean they've obtained a doctorate? I have no idea, right? Or like multiple doctorate level degrees, I don't know. What is a 50? I don't know what a 50 is, okay? So all they do is they've somehow, when they've collected their data, they turn this thing into a number from 1 to 100, and they don't actually tell us whether, what corresponds to a high school degree or bachelor's degree or whatever. They just do this, okay? There's a few other things. The year in which the immigrant arrived in the United States, the age at the immigrant's age at the time of immigration, and is the person fluent in English, yes or no, and is the person from Mexico, yes or no, okay? And so effectively, we're just going to see what's the relationship between this numeric value, the achievement, and this categorical variable, whether the person is Mexican or not, okay? And so here we go. This is just when you read in the data, we're going to look at this column, achievement, and this column for Mexico. And so using dplyr, I just do group by the variable Mexico and summarize, give me the mean and standard deviation, okay? And we get a mean of 64.5 for those that are not from Mexico, and 58.59 for those who are coming from Mexico. This is the standard deviation. So we see a slight difference here, and the question is this difference significant or not significant, right? And so normally we would be tempted to just apply a t-test here, and maybe that's okay, maybe it's not. We should do some, I don't know why this is hovering right here, but we should do some exploratory analysis, and that involves creating a few graphics. And so here I've got a box plot, okay? So this will be non-Mexican immigrants from other Latin American countries, and these would be the box plot for Mexican immigrants. And so it looks, I don't know, it's hard to say, right? Is there a significant difference? Maybe, maybe not, okay? This is just using the simple box plot command. And again, and here is kind of a estimated density plot. You guys are familiar with density plots? It's kind of like a histogram, except it's like smoothed over. And so, so you get something that looks like this, okay? I think next week we'll have some time to just talk about things that are fun. Well, I'll talk about how density plots are created. So this would be a kernel density plot. Okay, and so we can see we have like a spike here for non-Mexican immigrants, that kind of in this orangish red color, and then in the teal, I don't know, it's hard to picture, but this one looks a little bit more normal-ish, but both seem to have heavy left tails. Okay. The traditional analysis would just be to do a t-test, okay? And we would get a p-value of 0.03. When we do a t-test, what are the assumptions we're making here? Yeah, we're assuming that the sampling distribution follows a normal distribution, okay? And that basically means that your samples are large enough and that your population isn't so weird that this sample is big enough, okay? Yep, something happened. Okay, so for some reason I have this split up into a couple pieces here. So that's our, okay. I will, let me come in here and we'll do Parametric Bootstrap. In R. Clear all this out. So we have a total of 116 observations of immigrants coming from Mexico, and we have 34 for non-Mexican Latin American immigrants here. And so when we do this, this is our summary table, and we can just say, what is the difference that we get? We get a difference of 5.9. Okay, so if I just ask, print out the results. This is our summary table in dplyr, and we see the difference between 64.5 and 58.6 is 5.9 points. Okay, and so it's a so I write that the mean achievement level of non-Mexican Latino immigrants is 5.9 points higher than the mean achievement for Mexican immigrants. We want to know, is this difference statistically significant? Okay, and first of all, even before we answer whether it's significant, it's worth asking, is this difference even important? Okay, so even if the difference is significant, maybe this difference of 5.9 is not even important, and that's an important question that you need to ask, and statistics will not be able to answer. Okay, so we aren't even able to answer this question because we have our data dictionary doesn't tell us what a difference of 5.9 points even means. Okay, and we don't have the domain knowledge. Okay, I'm not familiar enough with the world of education or immigration or any of this to see, if a difference of 5.9 even matters. Okay, and so we could ask, here's one group of people and their average score in the class was, this is like saying, the average score of one group is 88% and the average score of another group is 89%. And maybe that difference is statistically significant, okay? But is a 1 percentage point difference important? And the answer is probably not, right? Like if people look, is there a difference between 89% and 88%? Is that difference important? Probably not, right? And we could, and so even if it is statistically significant, the difference may or may not be important, and we're not able to answer that question without more knowledge of the field, okay? But as statisticians, we can answer the question: is it statistically significant? And that's what we'll do, okay? So our null hypothesis will just be that the two means are equal, and the alternative will be that they're different, okay? Okay, we're ultimately trying to calculate the p-value, which is what is the probability of observing our data or something more unusual if the null hypothesis is true. And in this case, it would be, how often do two randomly drawn samples have a difference of 5.9 points or greater if both samples are drawn from the same population? Okay, so if the education achievement level is the same for all immigrants, whether they're from Mexico or not, could two random samples produce a difference of 5.9 points? That's what we want to know. And maybe the answer is, yeah, a difference of 5.9 points, that happens quite a bit. Or maybe it's a rare occurrence. We have no idea, okay? And so what we will do is we'll first start off by performing parametric bootstrap, okay? By repeatedly drawing two random samples from the same population, okay? And what we'll do is we will just make a crazy major assumption, okay? I don't know if it's crazy, okay? But we can say, in here, we can just start off by saying the population from which our data is drawn is normally distributed. That's going to be the big assumption here when we're doing parametric bootstrap, okay? And so in this case, it would make sense to use the mean value of all of our data. So this is everybody pooled together. If we throw all of the educational achievement levels of all the Latino immigrants into one pool, okay, which is effectively what we are saying in the null hypothesis. The null hypothesis saying is that everybody's value is coming from the same distribution, then it makes sense to just use the mean that we have there, okay? And then we throw in, and we get the standard deviation, and we're going to use these as our estimates of what the mean and standard deviation are in our parametric distribution. Okay, does that make sense so far? And then to do the parametric bootstrap, we are going to draw group A. We're going to draw 116 values from this normal distribution. And then for the other group, the non-Mexican Latino immigrants, we will draw 34 values from the exact same normal distribution. Okay, because here we are testing out the null hypothesis that they are coming from the same distribution, and we want to know, is it possible to get a difference of 5.9 points just from the random sampling? And so that's what we have going on here, right? Does this for loop make sense? Because this is effectively parametric bootstrap right here. We make an assumption about what our population looks like. In this case, we're assuming it's normal, and we're going to use the estimates from our data to define that normal distribution. And then we say, under the null hypothesis, both samples are drawn from the same population. And so we do that. We draw two samples from the same population. And then we say, okay, so I've drawn two samples. Let's calculate the difference between the means of those two samples and record how often we get a difference of 5.9 points. Is it okay? Can I move on here? Yes, question.
Why do you choose 116 and 34?
Well, because I'm choosing 116 and 34 because that is what my samples look like, okay? So I have a total of 150 people in my sample, and of those 150 people, 116 came from Mexico and 34 came from other countries. And when we calculated the mean of the 116 and the mean of 34, we got a difference of 5.9 points. And the question we're asking is, could I get a difference of 5.9 points just from random sampling if I were to repeat this random sampling process again? And so I have to kind of recreate the situation of my data, which has 116 in one sample and 34 in another sample. Okay, so I'm basically trying to just say, if somebody else drew data just like the ones I did, what would they get? And so I have to do 116 versus 34. I can't just say, oh, I feel like doing 100 versus 100, or 75 and a 75, or something like that, because then the properties of my resulting samples would not look like the samples that I'm testing against. Okay, so we'll go. I go ahead and I will run this. Okay, it's done. That's the parametric bootstrap is done now. And what we want to know is, okay, what is the distribution of these differences? I can ask for the summary of the diffs that we calculated. We calculated 10,000 of these. Okay, most of the time we're getting a mean of something very close to 0, and that makes sense, right? When you if you're taking two random samples from the exact same population, you would expect most of the time the difference between those two random samples means would be close to 0. Okay, and that's what we see. And we want to know, how often do we get a difference of 5.9? And we see, our third quartile is around 2. How often do we get a difference of 5.9? Well, we can ask, for a histogram of the differences. And we got a difference of 5.9, so that puts us right around here. And the question is this an unusual place to be or not? Okay. All right, and so to estimate our p-value, our alternative hypothesis is non-directional. So we've got the not equal sign. It's just saying that the education achievement levels are different. We're not assuming that one group of immigrants has a higher or lower achievement level than the other group. I mean, there's no reason to suspect that, at least from just the description of the data, okay? And so we're going to just see how many of our differences that we observed, the 10,000 in our empirical sampling distribution, how many of those are greater than or equal to the observed difference here? I guess I could put absolute value here, okay? But it's positive. So the inner part is going to produce a logical vector of true or false, right? This will just tell me how often true or false if my differences are greater or smaller. And then to take the mean of that, we'll get an empirical p-value, right? So here it says we get an estimated p-value of 0.0453. So what this is telling us is that even when we draw two samples from the exact same population, which is what we did that 10,000 times, it is possible, just from random chance, to get one sample and another sample where the difference between their sample means is 5.9 points or more. That happens from random chance alone. And that happens about a little bit less than 5% of the time from random chance. Okay. And so now we have to make a conclusion, right? So our conclusion would depend on the significance level that we're using. And what would you say? Would you say you are ready to say that the two groups have a different population mean, or that you are not ready to conclude that the two groups have a different population mean? Okay, well, if you just used a straight alpha of 0.05, what would you say? You would say this is significant, right? 0.0453 is smaller than 0.05. It's significant. We conclude that there's a difference, right? The question is do you want to use an alpha of 0.05? Why are you using an alpha of 0.05? And there's a lot of debate and a lot of question on the use of 0.05 and null hypothesis significance testing to begin with, and all of that. And so, you know, probably you'd say, I don't know. Okay, and again, a key part here for this was that, you know, is the assumption that the population follows a normal distribution okay? Maybe, maybe not, okay? This is the original, if we create a histogram of the original data, this is what it looks like. And does this look normal? I don't know, that's up for debate, right? If we create a QQ plot, does this look like a straight line? Oops, of course. You know, I don't know, it looks like we've got some trouble with our left tail, okay? This doesn't quite fit the normal, and so maybe our parametric bootstrap was doomed for being useless anyway from the start, because maybe it's not safe to assume we've got a normal distribution, okay? So it's a tricky thing, okay? Science is hard, statistics is hard too, okay? All right, let's, I guess I can start Nonparametric Bootstrap. We might run out of time. Okay. For Nonparametric Bootstrap, we're going to do the same thing, okay? Except we are not drawing, when we draw our random samples, we're not drawing from some defined parametric distribution like R norm. We're going to draw values by resampling the exact data that we have. Okay, so this internal part here of our loop, this part is very similar. Okay, we have the null hypothesis. The null hypothesis is that our two samples are coming from the same population. Okay, except the population is going to just be, you know, a billion duplicates of the random sample that we have. Okay, so instead of assuming that the population has a particular distribution like the normal distribution, we're making the other big assumption that our random sample is representative of the population. And maybe that's a good assumption, maybe it's not a good assumption, okay? And so what we will do is sample with replacement, which is effectively the same thing as making an infinite number of copies of our sample. And we do our test, which works the same way. We generate 2 random samples from our quote-unquote population, and we'll calculate the difference between the group means. So here I'm going to create a vector of differences to store my values. I'm going to draw 116 values from our population, a stand-in of the population, which is just going to sample with replacement. We say replace equals true. I draw another sample of 34 from the exact same population. I do sample from our values with replacement set equal to true. So here I'm getting 2 random samples drawn from the same population, except our population is not defined as a normal distribution. It's just defined as duplicates of our random sample, and I calculate the difference between those 2 randomly drawn samples. So I want to make sure that this code makes sense for the nonparametric bootstrap. Okay, the level of enthusiasm is okay, so we'll go ahead and I'll do that, and then I'm going to calculate my p-value by taking a look at the differences and seeing how often our differences are greater than the observed difference that we have. And when I do this, I get 0.0465, okay? Which matches quite closely to what I got when I did parametric bootstrap, right? So it's kind of an indicator that, you know, the assumptions we made for the parametric bootstrap probably weren't so terrible, okay? And so, you know, what do you do with this information? That's up to you, right? Empirically, it says we can get this difference of 5.9 points from random chance almost 5% of the time. A little bit less than 5% of the time, 4.6% of the time. And the question is, do we then have evidence that there is a difference or not? And I would be inclined to say I'm not ready to reject the null. Okay, that's me. I'm a little bit probably more cautious in terms of the alphas that I would use. And I would say this is at least interesting, okay? And I would say there might be something here. We probably should go out and collect more data rather than just jumping to a conclusion right now. So I'll say, you know, this p-value is suggestive. That might be the word I would use. Rather than statistically significant, I would say our difference is suggestive that more research needs to be done. And then who knows? Maybe they'll say this is something worth pursuing. Okay. Again, you want to ask, is that difference of 5.9 points even important to begin with? And that will probably factor into whether you will get funding for more research or not. Okay, if they say, well, 5.9 points, that doesn't even matter, nobody cares, and then no one's going to care. Okay, but they might say, oh, 5.9 points, that's kind of a big deal. Let's look into this some more. Okay, we'll end here for today. We'll take a look at a little bit more non-parametric bootstrap and stuff on Friday, and we'll see you guys then.